the cloud. All right, so now we're recording. So what I want you, I'm going to now share I'm going to make you the host. All right. Okay, so now you can share your screen. And you want to share the PowerPoint slideshow. Correct? All right. So now in about, well, when it gets to 7:59, you now will start the webinar. And what you'll see is at the bottom, the participants number will start to go up really quickly because they're all kind of sitting there waiting for it to start.
Got it.
And then we'll give it till exactly 8 o'clock or 11 o'clock your time. And then I'll very briefly introduce you and then you just go.
Okay.
And then I will be muted and off video. And Debbie we'll all be muted and off video, but we're in the background, so.
Okay.
All right, and people are starting to come in, you can see that now. Thanks everyone for joining us for our third day of the QMS course offered by Pathologists Overseas and ASCP. I'm Dan Milner, the Chief Medical Officer of ASCP, and today's speaker is Dr. Sarah Riley on process control, quantitative quality control, which will include some cases at the end. Please remember, if you have questions, put those in the Q&A box, which is at the bottom of your screen to the right. If you want to chat directly with us about a technical problem, you can use the chat box, but don't put questions there, just put technical issues. But if you want to ask a question, put it in the Q&A box. If during the talk, Dr. Riley asks a question to the general audience and you want to chime in with an answer, you can put that in the Q&A box or the chat box, either one. And we will assess that and she'll make comments about it. So without further ado, I'm going to turn it over to Dr. Sarah Riley.
Hello, everyone. It is really a privilege to get to share this learning opportunity with you. And I hope that this will be very beneficial for you. And I hope that we'll have a nice time and be able to answer any questions that you might have about this topic. So as Dan said, I am Dr. Sarah Riley. I am on the board of directors of Pathologists Overseas, and I am one of the clinical pathology program directors for Pathologists Overseas. I also currently direct a forensic toxicology laboratory and oversee a clinical toxicology laboratory section in St. Louis, Missouri, United States, which is where I live. And quantitative quality control is extremely important for all of clinical pathology and especially for toxicology. So this is a topic that is very, very near and dear to my heart, you might say. So I'm excited to be able to share with you. We'll go ahead and get started. At the end of today's presentation, you will be able to differentiate between accuracy and precision. You will be able to select control material for your laboratory. You will learn how to establish acceptable control limits for a method when only one level of control material is available. And you will explain the use of a Levy-Jennings chart. And we'll talk about how to create a Levy-Jennings chart as well. So quality control is a component of process control. It's a major element of quality management system. It monitors the processes related to the examination phase of testing, so the actual interrogative part of the testing system, and allows for detecting errors in the testing system. These errors might be due to the test system failure, or to adverse environmental conditions, or to operator performance. And quality control, or QC, gives the laboratory confidence that the test results are accurate and reliable before any patient results are reported. And in this presentation, we're going to talk about how quality control methods are applied to quantitative laboratory examinations. So quantitative tests are those that measure the quantity of substance in a sample and yield a numeric result. So these will tell you there is X amount or a certain concentration of an analyte in a sample versus just saying the analyte is there or not there, it's positive or it's negative. Since quantitative tests have numeric values, statistical tests can be applied to the results of the quality control material to differentiate between test runs that are in control or tests that are out of control. And this is done by calculating acceptable limits for control material and then testing the control material with patient samples to see if it falls within those limits. And as part of the whole entire quality management system, the laboratory must establish a quality control program for all of its quantitative tests. So every test that reports out an actual measurement, a concentration or an amount, needs to have quality control. Evaluating each run this way allows us to assure that the patient results are accurate and reliable. So the steps for implementing a quality control program are to establish policies and procedures to make sure that the test is done the same way by all of the staff every time, to assign responsibility and then train staff appropriately, to select the high quality controls, to establish control ranges, to develop graphs to plot control values, and these are referred to as Levy-Jennings charts, to monitor those control values, develop procedures for corrective action, and record all records taken. So if any corrective action is taken, documentation of that needs to be recorded. So we'll talk a minute about what is a control. Well, a control is material that contains the substance being analyzed. So if your test is for creatinine, then your control material will contain creatinine. And this is run, and the controls are run at the same time and at the same way as patient specimens. So a control is prepared along with patient specimens for a run and run along with that patient specimen at the same time. And the purpose of the control is to validate the reliability of the test system and to evaluate the operator's performance and the environmental conditions that might impact the system or might impact the results. And quality controls can be used to run after calibrating the instrument to assure that the calibration is correct, and then run periodically during testing to make sure that the test is what we say in control. So we talk about, in laboratory medicine, we talk about calibrators and we talk about controls. And these are both part of process management and quality management, but they are not the same thing. Calibrators are solutions with a defined concentration, and these are used to set or to calibrate the instrument, kit, or system before testing is begun. Calibrators are often, but not always, but they're often provided by the manufacturer of the instrument. They should not be used as controls because they're being used to set the instrument. So this is where you set your calibrator as a 2, then the instrument knows that that signal from that calibrator is what a 2 should be. On the other side, the control is a substance that is similar to the patient samples and also has an established concentration, And the controls are used to ensure that the procedure is working properly. So you set the instrument and then you test that with the control. Calibrators should not be used as controls because they are being used to set the instrument. If you use a calibrator as a control, then you don't have a way of testing that calibration. Calibrators are sometimes called standards. You might hear people refer to as their standard, but the term calibrator is preferred. And oftentimes a calibrator may not have the same consistency or may not be the same matrix as the patient specimen. Well, when you are picking a control material, you should pay attention to specific characteristics. So some of the important characteristics to consider when making a decision and choosing a control is the control appropriate for the diagnostic sample? So the control must contain the analyte that the test system is testing for. Again, if your test system is testing for creatinine, then your control needs to contain creatinine. The control values also need to cover the medical decision points. So they need to be in the normal range, in the high range, and the low range. And this is so that you can be assured that your test is accurately reporting values at those points where a medical provider is going to be making a decision on treating a patient. Also, it's important that the control material is similar to the test sample or the matrices are similar. So if your test is looking for protein in blood, then the control material should be made up in blood or something very similar. And this is so that you control for any matrix effects or any impact on the system that might be caused by endogenous material in the matrix. Another thing to consider is whether or not the control material is available in large quantity, ideally enough for 1 year if you have the capacity to store it under the appropriate conditions. One reason you want the control material in large quantities is that, as you will see as we proceed further in this session, that validating a control material is quite a process. And having to do it frequently can be very tedious, time consuming, and also consuming resources for your laboratory. So being able to purchase it or make it in large quantities and store it appropriately is very beneficial. But then again, you also want to be able to store the material in small aliquots. So ideally, you would have a large quantity stored in small aliquots. And the importance of the small aliquots is so that the material is not being frozen and thawed or refrigerated and brought to room temperature over and over. So control material is available in different types. It might be frozen, freeze-dried, or chemically preserved. The freeze-dried or lyophilized materials must be reconstituted, and this requires very great care in pipetting using a calibrated pipette in order to assure the correct concentration of the analyte. And sources of control materials it might be commercially prepared, so you might be able to purchase it from a vendor. You could make it yourself in what we call in-house. Or it could be obtained from another laboratory, such as a central or reference laboratory. And we talk about the different types of control materials. We refer to them as assayed, unassayed, or in-house. Assayed materials are ones that are usually purchased or perhaps obtained from a reference or central laboratory. These have a target value that is predetermined. So the laboratory is required to then verify that target value and then put the control material into use. On the flip side, there are unassayed control materials where the target value is not predetermined, and that a full assay to determine the target value is required before using the material. And lastly, the in-house control material is material that is created in your laboratory, usually by taking a pooled patient specimen and adding in the analyte of interest. And this requires full assay and validation prior to use. But an advantage to a laboratory using in-house material is that you can produce very large volumes with exact specification. It's important to remember that control materials are very often serum-based or blood-based, and so universal precautions need to be maintained when handling these materials. Even though they're not patient specimens, they still have the potential to be infectious. So again, when choosing controls for a particular method, it's important to select values that cover the medical decision points. For example, one that has a normal value, one that is high or low, but in the medically significant range. So if we look at this little picture here, the schematic, we have a patient sample. And this patient sample contains your analyte of interest. So we'll just stick with creatinine. We're talking about creatinine. So when the patient sample comes to you, the amount of creatinine in the sample is unknown. It could be in the normal range. It could be in the abnormally high or abnormally low range, or it could be in a critically high or a critically low range. So your testing system needs to be able to differentiate all of values in all of these different ranges. And then ideally, you should have control material that tests the system at these different ranges. When preparing and storing quality control materials, it is important to carefully adhere to the manufacturer's instructions for reconstituting and storage. And this is if you are purchasing assayed material from a vendor. If in-house control material is used, then aliquots of the material should be frozen and placed in a freezer so that small amount can be thawed and used daily. It is not a good practice to thaw and refreeze control material. And the reason for that is that the process of thawing and refreezing greatly enhances degradation of the material. So it seems like a hassle or it seems like a lot of trouble and work to freeze down small aliquots, but in the long run, it greatly stretches the longevity of your material. Also, the freezer temperatures or refrigerator temperatures need to be monitored and maintained in order to avoid degradation of any analyte in the stored control material. And again, a calibrated pipette, needs to be used to deliver the exact amount of required diluent to any lyophilized materials that need to be reconstituted. It's all about precision here. So using precise materials and tools to make your control material is very important. Once the appropriate control material has been chosen and purchased or prepared, the next step is to determine the range of acceptable values for the control material. And this will be used to let the laboratory know if the test run is in control or if the control values are not reading properly, if the assay is out of control. And the way this is done is by assaying the control material repeatedly over time. At least 20 data points must be collected over a 20 to 30 day period. When collecting this data, Be sure to include any procedural variation that occurs during the daily runs. So for example, you would record if different testing personnel normally do the analysis, and any testing personnel that would normally part of the analysis should be involved in the validation of the quality control material. Once the data is collected, the laboratory will need to calculate the mean and the standard deviation of the results. So a characteristic of repeated measurements is that there is a degree of variation, and variation could be due to operator technique, to environmental conditions, or to the performance characteristics of an instrument. And some variation is normal, even when all of the factors we just talked about are controlled. And the standard deviation is what gives you that measure of variation. So let's just go through this one more time using the schematic. So your control material is chosen based on the appropriate characteristics. Once you have chosen and purchased or chosen and made your quality control material, then we need to establish what the either establish or verify what the concentration is. And so to do that, the control is run 20 times over 30 days. Or within 30 days I think that's an easier way to think about it, to run a control 20 times within 30 days. And then from those runs, that data is processed to calculate the mean and also the standard deviations. And that gives you an idea of how much variation there is under normal circumstances when you're running in your quality control material. So variability is a normal occurrence when a control is tested repeatedly. So, and this is affected by operator technique, it's affected by the environmental conditions, and it's affected by the performance characteristics of the measurement. So the goal of validating your quality control material and then monitoring your quality control material is to differentiate between variability that's due to chance and what is due to actual error. So the variability of repeated measurements will be distributed around a central value. And the characteristic of this is called the central tendency. So if you look at this graph here, we have frequency on the x-axis and the measurement on the right. And out of these 13 measurements, there are different values that were obtained, and the frequency of those different values are what these bars represent. And you can see that the frequency, there's definitely a central tendency, or a point at which most of the measurements give a specific result, but there's some variation. So sometimes you get results over here and sometimes you get results over here. And if you look at the shape of this graph, it kind of looks like a curve, like a bell, like a bell. So this is a normal distribution and also referred to as a bell-shaped curve. This is an expected expected graph of variation. There are different statistical values that are used to measure this central tendency. The mode, which is the value that occurs with the greatest frequency. The median, which is the central point of the values when they are arranged in a sequence, or the value at the center or the midpoint of the observations. And then the mean, which is a calculated average or an arithmetic average of the results. The mean is what we use most commonly in laboratories to measure central tendency. So all of these are terms that refer to central tendency, but they can be different values. So if we look back at our chart here, the mean is calculated as a 5, but the mode, which is the most frequently occurring response, is 6. And then the median, which is the value that's directly in the middle of all of the values ranging from lowest to highest, is 7. So all measures of central frequency tendency, but not all the same number. And again, the mean is the number that we use most frequently in laboratory medicine to measure central tendency. When we're doing statistical calculations in laboratory medicine, there are some symbols that are used. You may be familiar with these, but we're just going to go back over them to make sure everyone is on the same page. So this symbol, or epsilon, refers to the sum of a certain number of data points. So this tells you, if you see this, it tells you that you need to add the data points. N usually refers to the number of data points. So if you run your quality control material 20 times, you should have 20 data points. Your N should be 20. X1 through Xn means all of the measurements 1 through N. So again, if you have 20 measurements, all of the measurements would be measurements 1 through measurements 20. And then an X with a bar over that stands for this, the mean. So when you see this, that you know that is referring to the mean, which again is the calculated average of the results. So let's focus on the mean for a second. Again, X with a bar over it is the statistical symbol for mean. And this is calculated by adding up the data points for each measurement, 1 through N, or if we're doing 20 measurements, then 1 through 20, divided by the total number of measurements. So again, if we're doing 20 measurements, we would divide by 20. So just to recap, the mean is equal to the sum of all of the measurements, the results of all of the measurements, divided by the number of measurements. So we'll go through a quick example of a calculation of a mean using an ELISA. So in this calculation, the control is run 20 times for 30 days. You would record both the optical density and the cutoff values for each measurement. So for each measurement now you have 2 values, optical density and cutoff. Then you would divide the optical density by the cutoff for each data point or observation, and that standardizes or normalizes the data. So each measurement is now a ratio of OD to CO. Then you would add all of these ratios together, so 20 ratios, and divide by the number of measurements, which would be 20, to get the mean. Also, when you look at your data, you can look for outliers. So the purpose of obtaining 20 data points by running the quality control sample is to quantify your normal variation and establish ranges for quality control samples. And you can also, sometimes when you're doing these sets of 20, you will be able to identify outliers. Outliers are values that are outside of what you are typically getting for your sample, and they're usually pretty obvious. If there are more than 2 outliers in your data points, there is a problem with the data and it should not be used. You should start it again after identifying and resolving the problem that gave you those outliers. So if we look at this set of 20 results or 20 measurements, for the most of the samples, the results kind of range from, looks like 185 is the low one, up to 212. But then we have this one result that is 270. So there's no other sample that comes anywhere close to 270. So this one is an outlier. And because there's only one outlier in this set of data, you can remove this and just proceed with calculating your mean. So when we were looking at our bar chart, I referred to normal distribution. And this is what normal distribution looks like if you were to smooth over those bars and just have that outline of a bell. This is, again, called a bell-shaped curve. It's characteristic of a normal expected variation. And this is what this kind of distribution is what we assume for all of our quantitative quality control statistics. So we expect our results to look something like this and not to be all, we don't expect the same result every single time. We expect a distribution that looks kind of like this. So getting back to why we're doing this because we want to monitor the accuracy and the precision of the assay. But what are accuracy and precision? The definitions are: the accuracy is the closest of the measurements to the true value. Precision is the amount of variation in the measurements. The less variation that a set of measurements has, the more precise it is. The more precise the measurements, the width of that curve, that bell-shaped curve, is going to be smaller, because all of the measurements are closer to the mean. And then bias is the difference between the expected test result and the accepted reference method, or the bias is the difference between the actual concentration based on the reference material and what you actually get. So it is sometimes easier to think about accuracy and precision when you look at it graphically. So here we can think about accuracy and precision reflected on a target with a bullseye. So in this illustration, the bullseye represents the accepted reference value, which is the true and unbiased value. If a set of data is clustered around the bullseye, then that data is accurate and precise. The closer the hits are together, they are precise. But here we have a set of results that are very close together, but they're not at the targeted value. So these are precise, but they're biased. They're biased to the right of the expected value. And then on this side, we have results that are not at the expected value, so they're not accurate. And they're also not precise, because you see all that scatter of the results. They're not closely grouped together. So this assay is imprecise. So an accurate result is one that is precise and not biased. To determine the acceptable variation, the laboratory has to compute the standard deviation of the 20 control values. And this is important because because when we have this normal distribution, then we can be sure that measurements will fall within one standard deviation of the average 68.2% of the time. They will fall within two standard deviations 95.5% of the time, and they will fall within 3 standard deviations 99.7% of the time. And knowing that this is true for all normally shaped distributions allows the laboratory to establish ranges for quality control material. Once the mean and the standard deviation are computed for a set of measurements, the quality control material that is tested along with patient specimens should fall within these ranges. So what is standard deviation? Standard deviation is the measurement of variation of the set of results. It is very useful in the laboratory for analyzing quality control results because we're comparing our results to 1, 2, or 3 times the standard deviation. And this is the formula for calculating the standard deviation. So again, this epsilon is the sum of, so you calculate the standard deviation by taking each measurement and subtracting from that the mean of all the measurements, raising this to the power of 2, taking the sum of those values, dividing them by the number of measurements minus 1, so 20 minus 1 would be 19, and then finally taking the square root of that result. Another value that is used along with standard deviation to monitor precision is the coefficient of variation. So standard deviation is used to measure the variation in the test, and the coefficient of variation is used to monitor the precision of the test. So this is basically the percentage of the standard, it's looking at the standard deviation as a percentage of the mean. So after you've calculated your mean and your standard deviation, you can then calculate the coefficient of variation, or CV, by dividing the standard deviation by the mean and multiplying that result by 100. The CV is used to compare methods. So when the laboratory changes from one method to another, or the laboratory establishes a new method, they can use the CV as one of the elements to compare the precision of the new method or an additional method to the one that's existing. And for most clinical laboratory tests, the value of the CV should be less than 5%. To monitor your quality control material, you should graphically represent the control ranges. And the way to do this is, again, you assay your control material over the 20 data points over the 20 to 30 day period. Ensure that your procedural variation is represented. That's the normal variation. Calculate the mean and 1, 2, or 3 times the standard deviation. So you would calculate the standard deviation and then multiply it by 1, multiply it by 2, and multiply it by 3 to come up with those values. Then a chart can be created. The chart should have the mean value so for this example, that mean is 190.5. That is represented in the middle of the graph. And then the values that are representing 1 standard deviation, 2 standard deviations, and 3 standard deviations are also indicated on the chart. So for this example, the 1 standard deviation is 192.5. 2 times the standard deviation is 194.5, and 3 times the standard deviation is 196.5. And then also, so that's on the plus side, but you also want to calculate it on the negative side, or subtracting. So this is adding the standard deviation, and you also want to subtract the standard deviation. So the chart should also contain lines for minus 1 time the standard deviation, minus 2 times the standard deviation, and minus 3 times the standard deviation. And this chart is called a Levy-Jennings chart. And then the daily control measurements are plotted. So here we have on day 1, the value was 192.5. That was plotted on the chart. On day 2, the value was somewhere between 184.6 and 186.5. That's plotted on the chart. And then on day 3, the value was very close to the mean. So you can use these charts to very easily visualize how your assay is running. Are you close to the mean? Are you close to one or the other? Are you running high? Are you running low? And how much variation are you seeing? And these charts should be labeled with the, I'm sorry, I need to go back up. 1 second. These charts should be labeled with the assay name. So if this is your quality control material for creatinine, then it should say creatinine. And then if this is your and then also the lot number. So if this is lot number 5, you would indicate that here, just so you can keep track of what you're looking at. And then interpretation of the Levy-Jennings charts or quality controls depends on the number of controls run with the patient samples. So interpretation is, that refers to the decision that you make when you look at your result for quality control. Is it in? Is it out? Is it acceptable to run my patient to report my patient specimens, or should I not report my patient specimens and try to troubleshoot why my quality control might not be in? If you have one control, that's good, and you can accept the results if the control is within plus or minus 2 standard deviations. But if you have 2 controls, that's actually better. You can apply a multi-rule system that keeps you from having to throw out a whole batch if one of your controls is incorrect. So if you bear with me for 1 second, if we go back to here, on this day, this run 2 was actually out of control because this quality control fell below 2 standard deviations. And according to this graph, there's only 1 control being used for this assay. And again, if you have 1 control, if it's outside of plus or minus 2 standard deviations, then the assay is considered out of control. And we can use our Levy-Jennings charts to detect error. So random error is variation in quality control results with no pattern. So the graph that we just looked at was there's only 3 values, so it's hard to tell, but it looks more like random error. There was no distinct pattern. And so here, the only cause for rejection is if it's outside 2 standard deviations. And then you can also have systemic error, which is not acceptable, and the source of that error needs to be corrected. So some examples of systemic error include shifts, which means that the control is on one side of the mean, either high or low, for more than 6 consecutive days. Or the graph might show a trend, which is also systemic error. And this is the control moving in one direction. So if it's heading toward an out of control value, whether running towards high or running trends low. So let's look at some examples. So this is an example of a Levy-Jennings chart that's been run over multiple days. And what we see, what this chart shows us is that there's been a shift around this day. There was a shift in the control measurements. So the controls started out running close to the mean and maybe a little bit low, but then there was an abrupt shift. They started running at 1 standard deviation above the mean or higher. So again, a shift in the mean occurs when there's an abrupt change, and it's followed by 6 or more consecutive quality control results that fall on one side of the mean, but are typically within the 95% range. So that would be typically within two standard deviations. A lot of times a shift might be caused by a incorrect calibration or the assay needing to be calibrated. Trends, on the other hand, occur more gradually, but continually, and move in one direction over 6 or more analytical runs. So trends might display values across the mean, or they may occur only on one side of the mean. On the 6th occasion, this is determined to be a trend and the results are rejected. So on this Levy-Jennings chart, we see very clearly a trend. The results are running right at 1 standard deviation below the mean, and then they start to drift upwards to the mean, and then 1 standard deviation above the mean, and slowly until they're approaching 3 standard deviations above the mean. So after the 6th occurrence of this drift upward, the assay needs to be stopped. No more patient specimens can be run until the cause of this upward trend is investigated and corrected. So for every test, we have what's called the measurement of uncertainty. And this represents the range of values in which the true value is reasonably expected to lie. In most situations, the measurement of uncertainty is estimated at 95% coverage. So that means the value that's reported is one that would be reported 95% of the time. So then the more precise, for most instances, a range of plus or minus 2 standard deviations is accepted as a measurement of uncertainty that is explained by random variation. But the degree of variation is also dependent on method use. Methods that are more precise have less uncertainty because the amount of variation included is within those 95% limits is smaller. Laboratories should strive to use methods that have the highest degree of precision possible and to always follow standard operating procedures. It seems like such a basic thing, but to really have that standard operating procedure that's followed by all of the staff is going to cut down on a lot of variation in the laboratory. So what to do if a quality control is out of control? Well, the first thing is to stop testing. The testing process must be stopped, and the technologist must immediately try to identify and then correct the problems. Once possible sources of error have been identified and corrections have been made, and those corrections have been documented, that's very important, the control material should be rechecked. If it reads correctly after this rechecking, then the patient samples, along with another quality control specimen, should be repeated. It is incorrect to simply repeat the testing without looking for sources of error and taking corrective action. The purpose of the quality control is to alert you to something being wrong with your testing system. And if you ignore it, you ignore a failure and you just repeat it and keep going, you aren't going to have the opportunity to fix fix flaws in your testing system. Patient results must not be reported until the problem is resolved and the controls indicate proper performance. To solve the out of control problems, it's important to identify the problem and then refer to established policies and procedures for remedial action. Some possible problems to consider when you have a quality control that is out of control is whether or not there's been degradation of the reagents or kit. So you would check to make sure that the storage of the reagent or kit has been within the manufacturer's requirements, that there hasn't been exposure to any environmental extremes or light. You also look at the control material degradation. One thing to consider is operator error. So was the standard operating procedure followed here, or was a shortcut taken? Was there failure to follow the manufacturer's instructions for the quality control material, either the storage or the preparation? Was an outdated procedure manual followed? Was there some sort of equipment failure? Or was there a calibration error? To summarize, a quality control program for quantitative tests is essential. It should monitor all of the quantitative tests. If you are performing a quantitative test in your laboratory, that test needs to have at least one quality control. There should be written policies and procedures that are followed by all of the laboratory staff. There should be someone who is appointed as the quality manager who monitors and reviews the quality control data using Levy-Jennings charts. Statistical analysis needs to be used to provide for good records. And there has to be provision for troubleshooting and corrective action. A quality control program allows the laboratory to differentiate between normal variation and actual error. The quality control program monitors the accuracy and the precision of laboratory assays. And the results of patient testing should never be released if the QC results for the test run do not meet the laboratory target values. So with that, we can start going through some questions. Dan, should I just open the question box or?
Thanks, Sarah. No, I will read them to you. I've been looking at them. So there's actually quite a few similar questions, so we'll group them together. So several people are asking about the standard operating procedures for preparation of in-house controls for chemistry or hematology, or pointing out the fact that in LMICs, supply chain is such that the delivery of internal quality controls for hematology or chemistry may be delayed or difficult, so it would be very helpful to be able to do in-house preparation. So how would you respond to that question of, is there a standard operating procedure or a standard way to prepare in-house controls or quality controls for chemistry and hematology?
So my answer to that would be, I mean, each lab has to write their own standard operating procedure. It is possible to make your own materials and then to write a standard operating procedure for how you did that. The basic process would be to take a matrix. So this could be pooled sera or pooled blood. So you would use pooled sera for chemistry or pooled blood for hematology. And then you could do two different things. You could either add in analyte of known concentration. That would be, we call that spiking. Or you could just measure an analyte that's already endogenous to the specimen. So for example, for chemistry, if you wanted to make a control for sodium, you could take pooled sera from 20 to 25 patients, and then measure the result for sodium in that pool that you just made. You would do that over the 20 consecutive days, calculate the mean, the standard deviation, the coefficient of variation as we discussed here today, and then freeze that down and use that as your control. You would also need to validate how long those pooled specimens can be stored without degradation of the assay. So you would do you would measure the results again over a certain number of days, as many days as you hope to store the material. And you could get that same data from your Levy-Jennings charts. So I hope that that answers that question. It can be done. It definitely can be done. And it's better to try to make your in-house materials than to use no quality control at all.
Great. And so there's three very similar questions about CV and 5% as the cutoff. So is there a reference documenting that the CV should be below 5%? Is there, well, let me just double check. And then so for an example is, in relation to HIV-1 viral load, where high positive controls give values of 100,000 CP per mil, can we still take the CV being less than 5%? So can you comment on that value of 5% for CV, how it's established, and any variance on that?
Yeah, so the 5% CV variation mostly comes from CLIA guidances. And as I said during the presentation, that threshold of 5% is a general one for most of lab medicine. However, there are tests where it is acceptable to have a CV greater than 5%. And you would have to establish what your acceptability is for your CV for your assay, depending on what the analyte is, and then whether there's any guidance by professional groups around that specific analyte. And in general, analytes that have a wider reference range or wider normal value can have a larger CV than analytes that have a very narrow normal reference range. So for example, electrolytes, sodium, potassium, they have very, very narrow normal ranges or normal intervals. So you want the CV there to be small, less than 5, because again, CV is a measurement of variance. So when a normal value is expected to be within a very small window, you don't want a bunch of variance. But when you're dealing with something where your normal range could be anywhere from 5,000 to 50,000 cells, the CV can be a little bit wider because there's more room for variation within that normal range. Does that make sense?
Yeah. Okay, a couple of other questions. So what if my 20 runs of QC don't follow a normal distribution?
Then you need to do it again.
All right. How do you determine which parameters you will calculate for measurement of uncertainty in a CBC?
I think I might have to think about that and then respond to you via email. I'm sorry. I'm not sure I can answer that question off the top of my head. I'm very sorry.
No worries.
I will follow up.
Okay. So how often should I do quality control?
So the quality control, and again, there are different guidances by different professional societies, but ideally the quality control should be run after there's been a major change to the instrument. So whether you've done preventive maintenance or whether you've recalibrated the instrument, and then it should be done periodically throughout as you're running patient specimens. And so it should be done at least once per shift, or if it is a assay that you don't use very frequently. So for example, we measure electrolytes in vitreous fluid in my lab. We only do this like once a week. So we don't run quality controls every single day. We run the quality controls on the same day that we run the patient specimens. We just run it once before the patient specimens to make sure everything's okay. If you have an assay that you're running 24 hours a day, 7 days a week, you're going to want to space those quality controls out. Probably I would recommend every 8 hours, but then again, you would use your Levy-Jennings charts to give you some guidance as to whether you could run them less frequently or whether you should run them more frequently.
Right. If a control to be tested should be similar to the patient material, how will lyophilized controls be reconstituted to achieve that?
So they can be reconstituted. You would just follow the manufacturer's guidelines. And this is kind of a flaw where sometimes your lyophilized material is going to be brought up in like saline or water, or but ideally if this is like a lyophilized serum, then all of those elements of serum are going to be brought back up into the they're going to be reconstituted with whatever diluent that you're using.
Yeah. Okay, so with regard to taking action on shifts or trends, so with a shift or trend, when do you take action? 3 points or 6 points?
So the general rule is 6 points. I think that as you are getting experience with your lab, you will start to identify what types of errors you frequently see, and you might take action earlier than 6 points. If you see a trend, you've seen it before, you know how to fix it, why wait for 6 points? You could stop it at 3.
Great. All right. Should one run a sample if the control passes but the calibration fails?
I'm not sure how the calibration could fail and the quality control could still be in unless unless it's something at the high end. I would not run my patient specimens if my calibration failed.
Right. Okay. What is the difference between precision and uncertainty of measurement?
So these are similar, but the precision. So they're both similar. They both refer to variance in the assay. The uncertainty of measurement tells you how close. The uncertainty of measurement tells you. Hold on, let me just make sure I'm saying the right thing. So the uncertainty of measurement is just reporting reporting the value that you obtained, and then also plus or minus 2 times the standard deviation, and you get that from the standard deviation, which is the measure of variance. So they are related to each other. The precision is how precise the assay is. As the assay is more precise, your uncertainty of measurement will be smaller. As the assay is less precise, your uncertainty of measurement will be greater.
Great. There are some equipment that have quality control charts plotted. Should we rely on this, or must we plot our own LJ charts?
I think in general that what those instruments are doing with those are LJ plots that are programmed within the instrument. I think in my experience, most of the time they're reliable. I would just verify them by maybe doing your own LJ chart for a month or two and just verifying that it's reporting the data to you in the same manner, so that you know what you're just be confident in what you're monitoring, and then you can just use the instruments graphs.
All right, just a couple more. Why must I repeat testing patient samples after QC failures?
Okay, so this is usually when you set up your run, you run the QC, you set up a batch, and you would run your quality control and a couple patient specimens. And if the quality control fails, then those patient specimens that have been run after the quality control should be considered incorrect because that quality control failed. So you would not report that. You would fix whatever problem you have that's causing your quality control to be out, and then you would retest those patient specimens. Now, there are situations where you could maybe run a quality control, but you might not have a patient specimen run at that or prepared at that moment. And then, of course, obviously, you don't have anyone to throw out. You just stop and evaluate why your quality control failed.
All right. So after having 20 data points, you identify an outlier in this data set. Do you exclude that data point outlier and calculate the mean with the remaining 19 points, or are you supposed to make another run to have 20 new data points?
So if you have 20 data points and there's one outlier, you can exclude that data point and just continue with the 19 data points. However, if you have two or more outliers, then you need to rerun the whole 20.
Great. And then the last two questions are a little bit related, and I feel the pain and perspective of these two questions. This perspective looks like it applies primarily to the chemistry lab. How can I adopt this to the medical microbiology lab and the anatomic pathology lab?
Yeah. So I think the problem here, I think that quality control in these other two labs is as Dan said, is painful. And part of the problem is that the types of testing that are done are much more manual. There's a lot more variables, and the results that are given are somewhat, there's more subjectivity in them than there is in a chemical chemistry lab. But I think still that some of the overall principles that we learned about here today can be applied. Just there might be some differences because of what the assay, what kind of testing you're doing in microbiology are, but the general rules of accuracy, precision, and setting up quality controls and monitoring those quality controls for all of your testing can still apply.
Yeah, and I would add for anatomic pathology, there are some unique, novel ways to think about creating quantitative aspects of process control for things like histology or special stains or immunohistochemistry, and that's through digital imaging. So for example, if you, let's say you're doing your control for just your H&E stain, or your control for your silver stain, or your control for an immunohistochemistry. Every day, when you run that assay, if you take a photograph of that in the exact same conditions and then keep that in a file where you take that photo every day, you can actually look at those images over time and start to see it fading or getting too dark or changes in quality. You'll be able to pick them out. So that's like a visual process control that doesn't necessarily have a quantitative element initially, but you can actually use software to evaluate the colors or to give you a score on that and do that. So that's a relatively new approach. It's not really in this particular set of slides or this discussion. It's going to be part of one of the case reviews that we're doing, is how to use these things in anatomic pathology. But there are some ways to do it. But as you're all aware, anatomic pathology is quite a subjective specialty, and things like temperatures or pHs or that sort of stuff you can do quantitatively, but at the end of the day, it's all about the visual look of the tissue and if the pathologist is comfortable with reading that. And so using visual based qualitative or quantitative approaches to your controls is a really clever way to do that. A couple more questions. I think we have time, so we'll just do a couple more questions, Sarah.
Yeah, we have time.
Why run quality control with a batch of patient samples and not run the quality control alone, so that in case it fails, there will be no need to repeat the run for patient samples?
So this is a very good question. And the reason for running quality controls together with the patient specimens is a very good reason. And this is because you want the quality control materials to be, the quality control sample to be prepared in the same manner as the patient specimens. And the best way to ensure that they are prepared in the same manner is to do them at the exact same time. And when I say the same manner, it's more than just following the same procedure. It is the same exact person, the same temperature, the same pipette, the same moment in time, everything. So if the quality controls are prepared as part of a batch, then you just have greater assurance that the quality control sample is being prepared the same exact way as those patient specimens. If you run the quality control separately, see if it fails or passes, and then prepare your patient specimens, you are introducing an opportunity for there to be a slight difference in how the patient specimens are prepared that could actually impact the validity of the results. It's a very small opportunity, but the opportunity is there, and we need to be as precise as we can in especially in clinical chemistry.
All right, I think we're good. We can move on to the cases. There's some questions about the APP. So I will say that we have some case reviews coming up in AP, and we will make sure that those address these questions about visual uses for process control. So I think we can go on to the case now, and go ahead.
Okay, so we will go on to some cases. Again, this is my, really quick, this is my email address if anyone needs to reach out to me at any time. But moving forward, I hope you've all had the opportunity to review these cases. These shouldn't be too difficult, but they're good exercises. So the first one is a scenario. There's an albumin assay in the hospital lab that uses a purchased calibrator and 2 purchased assayed quality controls. There is a low control and a high control. On Monday, Bob started his shift on the albumin assay and realized that there was not enough of the low QC material for the next few shifts. So instead of working on obtaining and verifying new low QC material, Bob decided to use the calibrator as the low QC. So that's the scenario. The questions are: define assayed control, describe the steps necessary to put a new control in production, and is it acceptable to use a calibrator in place of a QC? Why or why not? So let me just put that out to the audience if I can. Is there anyone who would like to answer the first question?
And if you want to answer the question, you can just type it in the Q&A box as an answer.
Yeah, so what is a assayed control? We'll just give a few minutes to see if anyone can answer. Okay, what about the second control? Who can describe the second answer question? Who can describe the steps necessary to put a new control into production? Oh, sorry. I see that. I see someone answered. A control with a known range of values is an assayed control. That is correct. So what are the steps necessary? Yep, assayed control is where the target value is predetermined. Correct. So when you're using an assayed control, you need to put that control into production or put it into use. What are the steps? Yes, so Patrick got it. The steps necessary are to run the control for 20 to 30 consecutive days, to have at least 20 data points, and then to calculate the standard deviation, the mean, the standard deviation, and the coefficient of variation. And then lastly, is it acceptable to use the calibrator in place of a QC? Why or why not? And somebody already kind of answered this, said no, he should prepare a new control and rerun the samples, which is true, which is right, but why is it not acceptable to use a calibrator in place of a QC? Exactly, George. It is not acceptable because the calibrator is used to calibrate the measuring system and not to check the equipment for accuracy and precision. That's exactly right. So here are the answers. Assayed control is one wherein the target value has been predetermined. An assayed control value must be verified before the new control is put into production. This is done by running the control 20 times over 30 days, calculating the average, the standard deviation, and the coefficient of variation. The coefficient of variation is used to measure the precision of the assay, and the standard deviation is used to monitor the performance of the control. And then lastly, no, it is not acceptable to use the calibrator in place of the QC. The calibrator is used to set the instrument, and the QC is used to check the calibration. If the calibrator is used as a QC, there is no second check of the validity of the calibration. Our next example touches on that the statistical analysis of quality controls. So I have provided you with, I think there's 12 results, not 20, I just went with 12, but results for a total protein. And asked you to calculate the mean, the standard deviation, and the coefficient of variation. So before we move into these results, can anyone tell me what if they did these calculations before the class, what they got for the mean, or what they calculated the mean to be? And we'll go through the calculation together. I just want to see if anyone was able to do it prior to the class.
So we have Nanjela Chindima, who's at 70.3.
That's right. Nice. Yeah, 70.25, 70.3. Good. Okay, so how you calculate the average. Again, the equation is the sum of all of the values divided by the number of values. In this case was 12. And that gives us 70.25, or if you round up, it's 70.3. That's absolutely correct. Again, the sum of all the values divided by the number of values. And then I kind of gave it away here, but was anyone able to calculate the standard deviation, and what did they get? Ah, yep, Linus. Okay, so he got the standard deviation as 2.8. And that is right. So I have explained it here in detail, but the equation again for standard deviation is this the sum of each value minus the mean of the values squared divided by n minus 1, or the number of values minus 1, and then the square root of that. So the best way to do this, if you aren't using like a program like Excel, is to make a table with all of your results, and then the mean, which we established as 70.25, 70.3 if you're rounding up, and then this value minus the mean, or the value minus the mean, and then you end up with another set of results, and then to take this value, x minus the mean, and square it. And so you end up with another set of values. and then that, the sum of all of these values in this column here, divided by n-1, and then the square root of that. So one thing I want to point out here is that as you get outliers, or as values are farther away from the central tendency or the mean, they
Sarah,
really impact.
Your camera has dropped down.
Oh, sorry. You really can impact the standard deviation. So as the values decrease or vary farther from the central tendency, for example, on this graph, we have the one of the results is 65. Then when you take the when you subtract the mean from that, you get a negative 5.25, and squared is 27.56, which is much larger than a lot of these other values. And again, the 75, we get an x minus mean squared of 22.56, and then a 74 gives us a 14.04. So the farther the values are from the central tendency or the mean, the more they are going to impact your standard deviation. And it's very easy to visualize that when you look at the values in this way. And then lastly, calculating the coefficient of variation is pretty simple. You just take the standard deviation, divide it by the mean, and then multiply it by 100. And the value here was 3.99. There might be slightly different you might have gotten slightly different results depending on whether you rounded here or not. Are there any questions about that before we move on to the next case? Okay. So the next case, our final case for today, is looking at some Levy-Jennings charts. We have a Levy-Jennings chart for a white blood cell level 2 control, and then for an AST normal control. So looking at these two charts, which assay is demonstrating a shift? Which assay is demonstrating a trend? And then we can talk about how each situation should be addressed. So first of all, who can answer the first question? Which assay is demonstrating a shift? AST, correct, Aubrey. So AST is showing a shift. It kind of had almost two shifts. So it started out around 60, went up, stayed up here for a little while, and then shifted back down, and now it's running down. So what are some things that can contribute to a shift? Yes, Patrick, Hannah, Maureen, Charles, they're all right. So when I see a shift like this, I always think about calibration. Was the assay recaled, or does it need to be recaled? That's not always the reason, but in my experience, when I see a shift, I immediately think of calibration and go there. We can talk about some other troubleshooting in a minute here. So which assay is demonstrating a trend? Well, that's obvious answer. If one is showing a shift, the other one is showing a trend. So the whole blood cell level 2, white blood cell level 2 is showing this downward trend. That is slowly approaching it went from the 1 standard deviation running around 1 standard deviation above the mean, and then it's slowly going down and approaching the -2 standard deviations. So how would you address a trend like this? or what are some things that could be contributing to a trend? And I would say this is especially true for cell-based controls. Anybody have an idea? Yeah, so the first thing I would think about is gradual deterioration of control materials. I would also look at my environment. So am I seeing, is there an increase in the humidity or an increase in temperature, anything like that going on in my environment that might be contributing to a trend? So here are the answers really quick. Just the AST assay is showing a shift. The white blood cell level 2 control is showing a trend. And some things that you can do to troubleshoot these are to check the reagent age, expiration, and storage, making sure that the storage, the way the samples are being stored, that there hasn't been any sudden changes in temperature, that the reagents aren't expired. And you need to think about not just the reagent for the control, but also not just the control material, but also the reagents used in the assay. And then check the calibration. And of course, also, make sure that the person performing the assay is following the correct standard operating procedures. And we got through that pretty quick. I'm sorry, that is all I had for today.
No, it's wonderful, Sarah. I think we do have some follow-up questions.
Sure.
We could just do those. And
yeah, I'm sorry, I took down my screen. I should have left it up.
No worries. Okay, so just a couple of questions. Is it possible for QC to pass on the analyzer but fail on the LJ chart?
That depends on how you have your assay set up and the rules on your analyzer. So that's why I said I would double, before I relied solely on the analyzer, I would double check it with an LJ chart that I had made myself. I know it's more work, but it's always better to really be sure of what's going on. So ideally, the analyzer should be reporting following the same rules for acceptable data, and then reporting the same trends that you would see in your LJ plot. But I would verify it first.
Okay. What corrective action or actions should be taken if there is a trend with the runs still behind within the acceptable range?
So again, a trend in a LJ plot is a change over 6 runs in a specific direction. So a consistent movement in one direction of the control material, and it doesn't have to be outside of the acceptable limit, the 2 standard deviations or 3 standard deviations. So I would still, even if my values were still within acceptable limits, I would still investigate why I'm having that trend, because obviously something's going on, and you want to catch it before you start having your QC fail.
Great. Well, that was all the questions we had, and we are at about an hour and a half, which is where most of our sessions are shooting, which is great. Thank you so much, Dr. Riley, for joining us today. I think this has been really helpful to establish the basis for this conversation, and we will be doing some cases that will come back to this topic in other lectures. The registration email for the next session will be sent out immediately following this session, so you should get that in your inbox, and that will have the case attached to it for this Thursday's session. So you will need to look at the case, and you also need to go and register for the site in order to get the link for that. The landing page, which I will resend with the registration for today's that's going out today. That landing page has the recordings for all the sessions on it, as well as all the links, but those links to register aren't live until 48 hours before the actual session. So you can wait for the email, but if you miss the email or you don't get it, you can always go to the landing page and register for the course about 48 hours beforehand, but you won't have the case. So if you're not getting the emails, let me know. Some of you, I think I got some box B requests and I wasn't able to do those because of the way the email was set up. So make sure that you've registered with an email where you can get those emails and check your junk and spam folders. I'm assuming all of you are getting it because you're all on, but if you know other people who aren't, to make sure they do that. So thanks everyone so much, and we'll talk to you on Thursday. And Sarah, you can just close the webinar.